Let us begin 8th lecture, and 8th lecture we will be continuing our discussion on finding value of driving force, and then we will start discussion on nucleation. Now, in the last lecture, in the 7th lecture, we have started from here, and then gradually we have moved to this particular expression, which is del G T, the temperature at any temperature below melting temperature. If I try to find out driving force, which is del G liquid to solid, I can express in terms of enthalpy of melting temperature, and del T, which is the undercooling, is nothing but the temperature where we try to find out del G is subtracted from melting temperature. So, all the parameters are known values and they are not complicated values. Okay. So, we get a very simple expression to find out del G T. Now, when we try to see this value, let us see how it can be modified, how it can be refined. Now, we like to see the refinement in terms of more and more better and better approximation for del Cp liquid to solid. Since in the beginning, while coming to this particular expression, we assume that these values, this del Cp liquid to solid, the difference in liquid Cp and solid Cp is 0, but that cannot be. So, that is a very crude oversimplified assumptions. Now, in order to get into more refined value of this, we need to spend almost about 3-4 lectures, but our intention is to get to the heat treatment part. Our intention is to get to the TTT diagram as soon as possible after understanding the basics of thermodynamics. We would be content with this, but before that we need to see whether we would be able to content with this particular simplified value. Now, there are many people who worked on this particular in this particular field in order to refine this value. For example, there are people like Hoffman, people like Thomson, Spivak, people like Professor Ramchandran or Professor B.S. Murthy. So, those people have tried a lot of other ways to refine this particular value. Now, we just look at few simplified, few refined expression. So, the refined expression, for example, if we consider Hoffman's model, let us only look at the expression. If I see the expression del G liquid to solid equal to del H m T del T T m square. So, this is one of those famous expressions which takes more refined treatment to that particular, the whole treatment what I have seen, and there they have not considered del Cp to be 0. Then there was Thomson-Spivak, where they say it's a more complicated expression. But if you see the beauty of those expressions, those are devoid of del Cp. They have assumed some value which is non-zero value, and they have done treatment to this whole operation, and then they have come up with a more particular expression where you see everything again becomes a measurable, easily measurable quantity. Del Hm T, del T is nothing but this del T, which is the driving force, Tm, and here also those terms are common, but the only thing is the basically those expressions is different. Now, if I try to see the variation, let us say somehow I could calculate the Cp, del Cp, which is experimentally found out value when we try to see the liquid to solid transformation, I would get a plot where this is del G liquid to solid and this is del T if I try to plot as a function of del T. Now, if I try to see this expression, since del Hm and Tm both are constant for a particular metal, I would get a straight line as a function of del T, which is a straight line equation. And these del T, here it is 0. What does it mean? It means if I try to replicate this same diagram here, this is G S, this is G L, then at this point T minus Tm is 0, that means del T is 0. As we go lower and lower temperature below Tm, I have increment in del T. Now, at the same time, if I try to find out experimental variation of del G, if I could find the Cp of liquid as a function of undercooling, I would get a plot like this. If I try to plot in terms of the plot would be, let us say, something like this. This is my, let us say this is my expression 1, this is my expression 2, this is my expression 3. So, this is expression 1, this is experimental. Now, if I try to plot these model values del G, the plot would be, if I try to plot this is expression 2, and if I try to plot this one, it could be like this. Now, interestingly, the only noticeable thing is, until this temperature, all those refined calculated value and then also a crudely assumed value, they are matching. And these value can extend up to 0.2 to 0.3 Tm. Why what does it mean 0.2 to 0.3 Tm? Let us say if this temperature is 1000 degrees Celsius melting temperature, this would be 800 to 700 degrees Celsius. So, 300 to 200 degree difference below melting point, I would get almost same value for del G, even if I use very simple approximation. Rather, going for that suggests, and also you would later see that most of our practical values would be lying in this temperature range. So, if I try to plot in terms of temperature, so then this particular temperature which is 0 is Tm. So, within this range 200 to 300 degrees Celsius range from Tm, below Tm, we have most of the reactions over. Okay. So, that means we do not need such kind of complicated expressions. Okay. We are okay with a simplified expression, since we are seeing that within the temperature range where I would be concentrating on would not make any difference even if we use very simplistic approach. And engineering does not look at a very, very refined thing most of the cases. It just takes a kind of value which will be useful for doing calculations and finding values which will be needed for getting a kind of range of properties specified for a particular application. Okay. So, we do not need those kind of complicated things, we will be okay with this. So, that suggests that even if we take very, very simple approximation, sometime those approximation would have a very, very positive effect on our engineering problem solving. Okay. So, I think we would be okay with this. We will also do some calculations later on. Considering these two things, you would see that yes, it does not make much of difference. Okay. Of course, if you go farther below the temperature, these will start making difference, but we do not need to go to that particular temperature zone, rather than we will be concentrating on this temperature. Okay. So, that is the contention of doing this particular thing, but of course, there is a special importance given to this particular treatment. Yes, those have a very, very scientific values, because we do need to find out sometimes the actual value what is there. Now, once we found out the driving force, now we need to see whether that driving force, how that driving force is going to affect the actual phase transformation. So, now once we finish discussion on finding value of driving force, let us get to the nucleation part. Okay. Now, when we talk about nucleation, now we would again consider single component system, solid to liquid transformation, and let us initially consider simple pure metal solidification. Okay. And when we do simple pure metal solidification, we can have, I am just drawing the same plot again, temperature G, now let us say at this particular temperature I have a solid. Okay. So, if we have this enclosure and let us say this is a closed system at a particular pressure P, okay, and which is nothing but 1 atmosphere, and if it is at temperature T less than Tm, initially when I take that liquid to that particular temperature, everything is liquid, and let us say the volume of this particular enclosure is NV. VL. Now, in that particular enclosure, I will have a situation there I will form a nuclei, which is a small, I would say initially it can be considered as a kind of cluster, where from liquid it transforms to solid of volume Vs. Okay. And it could have different shapes, either it could have spherical shape, or it could have a lenticular shape, or it could have a cylindrical shape, any shape is possible. Okay. So, initially let us say let us assume that it is cylindrical, it is spherical. Let us say it is spherical. So, whenever we talk about spherical, so that means it is a sphere and it will have a radius r. Okay. Now, that means at that temperature, if we keep that liquid of volume VL, it will make change due to solidification, it will form a solid of radius r and it will have spherical shape. Now, so now this is a stage 1, this is stage 2, and if it is a liquid, then I can consider some free energy value of liquid, okay, at that temperature, and these free energy value would have unit as joule per meter cube. Now, how would we get this? Let us say if I know the Vm, which is meter cube per mole, and initially if this is expressed in terms of joule per mole, I simply get this by joule per mole divided by Vm, which is mole per meter cube, sorry, meter cube by mole. So, then I would get joule per meter cube. So, that means it is a volumetric free energy, and this also tells something. This volumetric free energy is coming from the volume of the material. So, that means it is considering the energy that is available from a particular volume of material. Now, similarly, if I have solid, so I can consider that is Gs. This is also the unit is joule per meter cube. Now, I can calculate what would be the total free energy of this particular closed volume. I can calculate the total free energy of this particular closed volume, and there interestingly the volume of liquid is now VL minus Vs, because I have also taken consideration of a solid. And interestingly, I am considering that VL to Vs whenever this transformation takes place. So, let us say this is V prime. So, that means this volume of liquid. So, this volume of liquid is converting to this volume of solid. That time I do not consider any volume expansion. Is nil. So, that means I do not have any volume expansion. So, that also makes my treatment easy. So, always we try to find out some, try to see some assumption within the rightness of that particular treatment. We have to make those assumptions in order to make things simple. So, now if we assume that, then so actually my transformation is from this to this. So, this is stage 1, this is stage 2, and if you see that stage 1 is entirely liquid, this line, and stage 2 I have solid here, at the same time some liquid. Now, if I try to find out what is the total free energy total at stage 1 is equal to VL G L. Similarly, G total at stage 2 equal to V L minus V S G L, because this is the volume of liquid that is remaining to convert to solid, plus this V S into G S. Now question is, does it end there? And another interesting thing, this also tells, because we are adding it up, the thermodynamic state function, we are adding it up, it also says that free energy is nothing but the extensive properties. Now from there we stop here, but would it stop here? Now there is one interesting part now. See, whenever I am creating a solid, as per our phase definition, I am seeing that in this particular cases, everywhere the composition is same. Here also the composition is same, but the structure is different here, structure is different here, because whenever I try to see the solid, that means I am talking about the crystalline solid. So that means they have a regular arrangement of atoms, and whenever I am talking regular arrangement of atoms, that times there is an interface which separates the regular arrangement of atom zone from a random arrangement of atom zone, if we consider liquid atoms are randomly distributed. That times I do create an interface. Fine. Now let us blow it up, this particular section. If I blow it up, this is my blown part, this pair. So I do draw all those lattice planes of a crystal. I have drawn those lattice planes. Now if I see, and if it is a regular arrangements, and if I consider that this length and this length is a 2-dimensional lattice, this length and this length both are same. Now at some point I do have missing part. For example, this is not of the same length of this. So if I extend it, then only I get a lattice. Okay. Similarly here, if I extend it, then I will get a lattice. If I extend it, then I will get a lattice. So these are forming. Now here I have created the interface, and we have said that the liquid atoms are random. So there is no regular arrangement of atoms over a 3 dimension in a long range distance. So that means at this place so this one, this one, this one, this one and this one. See, if we consider only this part, these lengths are breaking. And whenever I break any arm, what does it mean? It means that I am exciting that particular region. And now whenever I excite that particular region, that means I am increasing the energy of the system. So that means whenever I have an interface, as if I can say that arms are broken, and if arms are broken, I have enhanced the energy. So this particular line increases the system energy. So if something increases the system energy, that we can consider as a positive energy. Okay? And interestingly, this difference in energy is a negative energy, and the negative energy is always good because it goes down the energy hill and it talks about spontaneity. The process is possible, but creating energy or creating a kind of interface with a higher energy is not a spontaneous process. We are breaking it off. So that means this reacts against to this free energy lowering, because it imparts positive energy. And these particular energy, positive energies around the interface, and this interface is having some area which is, let us say, A surf, that means surface area. Okay? And along that surface area we have an energy we call it interfacial energy, which is, we call it gamma. And this gamma is different than the gamma we consider in case of FCC. So, in order to make difference with the gamma, FCC gamma in iron, which is called austenite, or FCC gamma in alpha aluminum, which is nothing but the aluminum single phase alpha, we put it as SL in case of solid liquid. So, that means whenever I form a solid, I do create an interface and I do have interfacial energy which tries to increase the system energy. Okay. So, now here the story does not end, because since I have created an interface, I do have to consider the interface energy part, the total interface energy, which is AS into gamma SL. So, that means at stage 2 I have these many energy terms. Now, if I consider to be G1 and this is G2, which is final, this is initial, I can find out what is the difference in energy. Okay. So, in order to find that difference in energy, so del G, which is the difference in G2 minus G1, equal to VL minus Vs GL plus Vs Gs plus A surf gamma SL minus VL GL. So, then I would see that this term and this term goes out. Now, this term and this term goes out. So, I would be left with Vs minus GL minus Gs, or I can say Gs minus GL plus A surf gamma SL. So, this is del G of this. So, now this is a very, very important expression. Now, if we consider a spherical particle forming in the spherical solid forming in the liquid, this would be 4 pi 3 RQ Gs minus GL plus 4 pi R square gamma SS. Now, this is extremely important expression, and now you see this is what? This is nothing but del GV. So, this is 4 pi. So, I can convert this particular term, I can write this particular term in the form of del GV. And this del GV, there is a negative term inherent to it. I can take this negative term out. So, this is my expression where I will be working on. Rather, we will see that from this we get an expression for the nucleation. Okay. So, this is expression, and also you see this del G is the difference between stage 1 and stage 2, and this del GV is the difference between liquid to solid transformation. So, that means this is my driving force, and this whether that solid would form or not, because this is the positive energy, this is the negative energy, finally where the system would go for this transformation would be decided by the negative value of this. So, we finally have to see what we have to see, whether del G going to negative values. So, that will tell me that whether transformation would actually take place or not. Now, we have to see that whether del G, these del G goes to negative in order to have transformation, because these tells me that there is a spontaneity, but this term is acting against to this, and this term has to overcome this particular positive energy term. Finally, it will create the condition that whether del G is negative, and that time we will have actual nucleation. Let us stop here. We will continue this discussion in our next couple of lectures. Thank you very much.